In this lecture, we're finally going to get on to spin and what it is. And it is a very complicated subject to get into your head. Some of the maths is fairly okay if you're being able to keep up with the idea of superpositions in quantum states. Spin is actually quite easy to deal with. But let's rip the plaster off really quick and just get to the point. No one knows what the spin actually is. We just don't. It's some kind of intrinsic angular momentum associated with particles and electrons, protons, whatever it is there. We can measure it, but we don't know what it is. It's actually easier to discuss spin in terms of what it definitely is not. For instance, it's not a physical spinning of the particle. The particle or an electron cannot spin for a couple of reasons. One, in quantum mechanics, we kind of model these particles as infinitesimally small points. So a point that doesn't have any extent whatsoever actually can't rotate. It's meaningless to talk about it rotating. But if we were to model it in a different way that says the electron definitely has a size and it's a ball with a radius, and we plug the radius in and its mass and how fast it should be spinning, we find that the surface of the electron is spinning faster than the speed of light, which cannot happen. There is an upper speed limit in physics about this sort of thing, and it just doesn't work. Doesn't work. So finally, if it was spinning, it would lose energy and eventually stop spinning. In fact, the fact that atoms don't do that and electrons that orbit around an atom don't do that is why we have quantum mechanics in the first place. And so spinning electrons or particles with spin definitely don't do that either. It's also not quite like a simple bar magnet. If we have a particle and we say it has a spin, we can sometimes be quite cheeky and say it's got a north and south pole to it because it generates a magnetic field. It has angular momentum and it is charged, so it generates a magnetic field. But it's not like that. Magnet can orientate just anywhere. Its orientation is always quantized. And a little bit like with orbital angular momentum, but when we measure it, some odder things start happening. So we can give it a direction, but it's not quite the same as orientating a vector in 3 dimensions. So for instance, if we were to orientate a vector in 3 dimensions, we need 3 components, let's say x, y, and z. Spin, we can effectively orientate it in any direction using only 2 directions, only the up and then the down direction. We can orientate it in any direction using combinations of those, which is a little bit weird. It is easier to talk about where it comes from though. So this is the Schrödinger equation. It's the time-dependent version, so it's got a slight change here to what you might be used to. This is called the energy operator, and I've highlighted in green where the problem is. If you know anything about relativity, the whole Einstein equals mc squared stuff, you might be aware of the term space-time. In relativity, you need to be able to swap space and time around. You have to treat them the same. They can be interchanged. We talk about time being the 4th dimension, and it can be treated like a spatial dimension, which means anything you do to space, you must be able to do to time and vice versa. And the Schrödinger equation, with respect to that, is wrong. So perhaps you can see why it's highlighted in green there. This here is a second derivative with respect to space. This is a first derivative with respect to time. We're treating time and space differently in this version of the Schrödinger equation. We can't do that in quantum mechanics. So along comes Paul Dirac, the smartest, nerdiest, most autistic man to ever live, as far as we can tell, and he said, well, I can fix that. And he comes up with this absolute beast of an equation that will probably scare the pants off most chemists. But okay, we can unpack a little bit about what it's doing. Well, we can see here we've got a first derivative, and then again first derivative due to time. So okay, that's looking fine. What's it doing over here? What's that equation really doing? And what we can see is, instead of taking a second derivative to make kinetic energy, Dirac's equation is just doing a first derivative. And that's momentum. So this is momentum, P, or a momentum operator. And he's summing up momentum over the x, y, and z directions. So this is a sum over 3 directions, x, y, and z, sometimes 1, 2, and 3, whatever this n is, we're summing up. And then over here, we've got mc squared. Now, if you're used to reading E equals mc squared, you'll recognize that. So, good, we're probably dealing with something to do with relativity here. And if you look up why this is wrong and the full version of this equation, Dirac's equation starts to at least look a bit more familiar. You can see how he's combining that rest mass and momentum to create kinetic energy. But it is not quite that simple. If all it took was to combine E equals mc squared with the Schrödinger equation, Schrödinger would have done it. We knew that in the 1920s. We could have done this a lot earlier than Dirac did it. Dirac's addition is to have these two things here, alpha and beta, and those are matrices. We're not going to go into them because we're not doing matrix mechanics until the next course, but they imply new properties of an electron. The first property it implies is that the electron can have a positive charge. Okay, so that makes no sense to a chemist. An electron has a negative charge, but a positron has a positive charge and is otherwise identical to an electron. So this equation here implies the existence of antimatter, and it did so years before antimatter was discovered, and then sci-fi went ahead and ruined it. So Dirac here is doing quite a bit of predictive power with just some relatively simple maths, at least by physics standards. The other property it implied was that the electron must have a new degree of freedom, and we'd eventually go on to call that spin. The electron can either have a plus a half spin or a minus half spin. And if you go around and read the history books about this, it's quite interesting how scientists of the day were really dancing around the concept of spin, and we had experiments that kind of implied that it was there, and they weren't quite putting 2 and 2 together yet. And so it took until maybe the 1930s to really get to grips with this. Dirac kind of put that all together and predicted it, and a few years later everything was kind of packaged up in a neat little box and we called it spin. Anyway, that's where it comes from. You don't need to worry too much about it. The maths is a bit involved by chemistry standards. So let's recap orbital angular momentum, which is what we did last time. If we have L equals 1, we know the angular momentum is quantized as 1 unit, and we can direct that up by +1, we can direct it down by -1, or 0. We can have it in completely the XY plane. Spin does something very, very similar. We're now not going to worry about what it is or where it comes from, but we're just going to look at its effect. Spin does exactly the same thing, except S is equal to a half. And now ms, exactly the same thing as before. Ms can go from plus s all the way down to minus s. Well, that can only be plus half and minus half. Sorry, sm, ms equals 0 can't happen. There is no ms equals 0 in this case. It would be if spin is equal to 1, but that's a different branch of subatomic physics that we're not interested in, or it belongs to composite particles. So you'll find S equals 1 when you do atomic spectroscopy and you're combining electrons together. In this case, we're not going to do that. We're just sticking to S equals a half, so we've only got an up or a down. So we refer to these as spin up, where things are plus a half, or spin down, where things are equal to minus a half, and they're used with different terms depending on what we're talking about. So all of these could refer to spin up and spin down, depending on which textbook you read or depending on which website you're reading. I'm going to mostly stick with this kind of notation, the up and arrows and down arrows, because they're easy to read. We know which direction the spin's spinning, even though it's not actually spinning in that direction. And we also have this alpha and beta terminology, which we will use when we do NMR, because that is the traditional way that NMR spectroscopy uses it. And again, for completion, I've added the Dirac notation. just for completeness, just so you can see it, we're going to cover what that means next term when we do this matrix mechanics. That has a more useful approach when it comes to spins, because spins are discrete states. We can't actually say psi is equal to some kind of function when it comes to spin. It doesn't really work, but using it with Dirac notation and matrices makes a lot more sense. So anyway, what even is spin, and what happens when we try to measure it? Well, spin can have any direction, x, y, or z, and whenever we measure it in a particular direction, it will always have the same value. It has a half. Or if we measure it again, it might be minus a half. So if we keep measuring particles in this direction, let's call that the z direction, we either find it to be plus a half or minus a half, one or the other. If we measure it to be plus a half and measure it in the z direction again, it's always going to be plus a half again. We keep measuring the same thing again. It's almost like we've locked it out into that direction, and it will always be right. And the same thing, if we found it to be the other direction, we keep measuring it, it would be the other direction. But if we've measured it to be in that direction and we swap directions to be, say, the y-axis, suddenly we go back to uncertainty again. We find it either plus a half in that direction or plus a half in that direction, 50-50 chance. So if we've got it in that direction and we switch back to measuring it in the z direction again, we'll either find it in that direction or that direction, 50-50 chance. That's the weird thing about spin. Whenever you measure it, it's always quantized. It's why its bar magnet kind of properties, it's modeling it like a bar magnet would not really work. It has a lot of uncertainty in its direction. So what it means to say that we've measured it in this plus a half direction up here means we have no information about the directions it is here. So if we measure it in those directions or any arbitrary direction, it basically it's random. It's a random chance. But the measurement of the value is always the same. We can't, for instance, point a spin out in that direction and then measure that or measure that. It will always be one or the other. That is why we started with the idea of polarized light, because when we did polarized light, it was a case of, does the particle fit through the polarizing filter or not? It's one or the other, and it is based on quantum states. Spin basically works the exact same way, except it's measuring a magnetic field, this property of spin, the angular momentum associated with it, in a particular direction. So how do we start quantifying how to build that in a particularly different direction? Because we know we have spin up and spin down. We have these states, and we want to describe a state that is facing the other direction. So just as before, we take a superposition. So we add them together. We take those states and we create a new one by adding them. We will, however, have to normalize it. We want the probability of finding one to always add up to 1, and we do that with 1 over square root 2. And we can check the probability of that by working out the square of these components. So let's square those coefficients. 1 over root 2 squared is 1/2. So we have a probability of up being 1/2 and probability of down being 1/2. That's exactly what we saw previously. So we orientate a spin in that direction by detecting it or measuring it that way, or letting it sit in a magnetic field that's in that direction, and we measure it at a 90-degree angle to that. So we've orientated the spin that way, but we're going to measure that way. The probability of it pointing up is 1/2, the probability of it pointing down is 1/2. So that equation to describe a spin in a different direction makes sense. We can define the opposite direction as well. So previously that said pointing left. Here I'm going to do pointing right, and all we've changed is we changed that plus to a minus. We've taken the other linear superposition here, or the other linear combination. So we're either adding or we're subtracting them. Again, check the probability. 1 over root squared is 1/2. minus 1 over root squared is a half. The negatives will cancel out. So we get a probability of a half again. And that is exactly the same as before. We've orientated a particle in that direction. We're measuring it here, and a 50-50 chance of finding it up or down. And that holds true if we swap our direction. We can change the basis. We can pretend that left and right is the basis. There's nothing special about up and down here. We can just do left and right instead. In which case we can describe the spin up as a linear combination of spin left and spin right. And that all works out. The maths will be the same. So if we orientate a spin up and we measure left and right, we've got a 50-50 chance of finding it left or right. And this is the one that really may provide a bit of confusion to you. We can add the third dimension by adding in imaginary numbers. Remember, I is equal to square root of minus 1. If we put that in there, well, if we square out that I, remember we're actually doing the complex conjugate. So when we do I times I, we actually do, oops, run out of space there. We're actually doing I times minus I. So all of those probabilities still come out as plus a half. The imaginary units get cancelled out there quite nicely. So if we want to describe a state that is facing towards us, we can take a linear superposition or a linear combination of the up and down, but we throw an imaginary unit in there. So that means we can orientate a spin in any direction using only states that are described as spin up and spin down. And that is a consequence of all the uncertainty. All we know about spin when we describe it as spin up and down is that it's pointing up or down, sort of. We know nothing about how much is in that direction, the left, right, the forward, the back direction. Absolutely nothing. There is no information that we have about that. It's entirely uncertain. So let's recap spin. It's weird. Sorry, it's weird. It's very hard to describe what it is. We only know what it isn't, and then there's a bit of maths around. So if you really want to do some wider reading on that, find Leonard Susskind's lectures or his book Theoretical Minimum. He starts with spin and explains it very slowly. He does dive off into the matrix mechanics, which we're not going to touch just yet, but it's a really clear explanation about how things work. It takes about 100 pages though. The maths describing that is relatively straightforward. If you can wrap your head around the superpositions used in polarized light, same arguments apply to spin, but instead of measuring polarized light in the left or the across or the up directions, we're measuring spin in the up, down, left, right, forward, backward directions. So we have two basis directions, and then superpositions of that can orientate the spin. And this is where, like, pretty much every equation that we come across in quantum mechanics looks the same. Some kind of coefficient and a wave function plus another coefficient and another wave function all build up to a quantum state. All we're saying here is that that must be a particular spin. That's another spin, providing they're in opposite directions, two coefficients, and then we can point the spin in any direction. Working out what that is for an arbitrary direction is not as straightforward as it seems. It's not like plugging in sine theta. We need to go into matrices to do that, so we're not going to do it just yet. But that's hopefully the intro to spin. That is what you need to know in order to understand magnetic resonance, which we'll get onto soon.